In this video, we're going to combine the facts we observed about current in the last video to write a single equation that describes current in diodes. This slide's replicated the circuit model and IV curve we had on the very first slide of this lecture. And that IV curve, it's pictured here, is consistent with the diode equation I've included on the right. The diode equation combines the exponential probability of transit that we talked about when we were looking at diffusion, and it subtracts a constant from that to represent the constant amount of drift current, which is independent of the applied diode voltage. And the diode voltage is up here. This total sort of current transit probability is multiplied by a new parameter called the dark current, which is labeled IS. The dark current is a device parameter that's affected by the doping profile, and calculating it relies on the built-in voltage. It indicates the amount of diffusion and drift that are present with no external bias. It's called dark current because photons that impinge on p-n junctions can also create free charge carriers, which, by the way, is how solar cells and photodiode works. So you measure this amount of current by keeping your p-n junction in the dark. And that differentiates these electrical effects from optical effects on the p-n junction. There's one common simplification to the diode equation that we're going to use liberally in this class. It's common to define a constant called the thermal voltage, which we'll abbreviate as phi th, and it's equal to kT over Q. The thermal voltage is about 26 millivolts at room temperature, which is easy to remember and easy to compare against measured results in lab, so it's a handy shorthand for us. And by the way, we're going with phi th as opposed to VTH because we're saving VTH for a parameter called the threshold voltage that we'll get to later. Finally, the IV curve that we've drawn up to this point doesn't capture breakdown behaviors, so I've added avalanche breakdown to the curve on this slide. So this is roughly what avalanche breakdown would look like. When the reverse bias causes the peak electric field in a p-n junction to rise to the point that minority carriers dislodge other minority carriers during their transit, then you get a chain reaction that causes a rapid increase in current in the diode. Remarkably, this process is reversible as long as the high current doesn't light the diode on fire with Joule heating, so with just sort of like I squared R kind of temperature increases. So avalanching and other related breakdown processes are actually reliable enough that they're deliberately designed into some diodes. Most notably, Zener diodes use a process called Zener breakdown to make reliable voltage references. So in summary, the diode equation, which is pictured here, combines diffusion and drift. So this is a diffusion term. It's exponentially sensitive to the applied voltage, and this is a drift term. It doesn't care about the applied voltage. The thermal voltage simplifies the diode equation, and it's about 26 millivolts at room temperature. We define the thermal voltage as being kT over Q. And avalanche breakdown happens at large reverse bias.